Now see here boys, today's topic is moment of inertia of given rod. How we can determine the moment of inertia of a given rod or any lamina. Now you see here, as we know that about the given axis, as I have already explained you, that moment of inertia means this is the ability of a body to resist the change in state of its motion. It may bigger the mass of the body, bigger will be its inertia, greater will be its inertia. It means more force is required. Now, if moment of inertia is the product of mass of the body and square of the perpendicular distance from the axis of the body. If about this axis, this mass m is rotating around this axis, this mass is rotating like this, then the rotational inertia of this body can be written as mr square. The derivation of this part we have already discussed. Now here you concentrate that how to determine the moment of inertia of a body of mass m about an axis, and this mass is placed at a distance of r. It will rotate about this axis like this. This is the axis of rotation. So the moment of inertia this body will be mr square, is mr square. Now you see here, if you are asked to determine the moment of inertia of a rod of mass m and length L and length about an axis passing perpendicularly to its length, perpendicular to its length, and to its one end of the to its length and through one of its end, through one of its end. No, through one of it. This is the first topic. Through first topic is first one is through one of its end. Now this is the first part. This is the rod. What is the mass of the rod? M, and its total length is L. Now this is the axis of rotation. This is what? This is axis of rotation. It means that if any rod is there, this is axis. It will rotate like this, because this part is one end of this rod is attached here, clamp here. It will rotate like this. It will rotate like this over this. So what is the inertia? See here, this is axis of rotation. Axis of rotation. Now you see here, as we know that moment of inertia is equals to mass of the body and square of the perpendicular distance. Now see, since the rod is clamped here, so this part is also in connection with the axis, this part, so several parts are there. The distance goes on increasing. So we can say that various parts of the rod are lying at a variable distance. Let me take, we are moving from here, this is 0 and this is length L, that is complete length of the. We are moving from here to here, to distance x. And at a distance x, we are taking very small portion of the rod. whose length is dx. Dx means just close to 0. It means this part will be here only. Here only. But for the mathematical expression, we are showing you that this part is slightly, so that it may be visible to you. But actually in practical sense, this length will be just close to 0. So this length is very, very small. We can take in only this shaded part of the rod, whose length is dx. Now the mass present in shaded portion. Mass present in shaded portion. Present in shaded portion. Shaded portion. Is this is dm. A small mass. A small part of the mass. Because see 0 to L is the total length of the rod. And the mass present over the total length of the rod is m. Now, what is the mass present over this small part of the length of the rod, which is dx, is dm. M is the mass of the rod and L is the length of the rod, mass parent length of the rod. Mass parent length of the rod. So mass present in per unit in length dx will be m by L into dx. Now, how we will derive the formula? Let we take a small length dl dx of the rod and its moment of inertia about the given axis will be how much? We know that moment of inertia is the product of mass into square of the perpendicular. What is the mass? And since we have to calculate the moment of inertia due to whole rod, due to very small part of this rod, moment of inertia will be di. Di is the moment of inertia of that portion of the rod whose length is dx. So di is equals to what is the mass of this portion? Dm. And what is the perpendicular distance from axis of rotation? X, square of the perpendicular distance. Now in place of dm we can write like this: m by L into dx. This is dm into x square. This is the moment of inertia due to very small portion of the rod. Similarly, we can take several portion of the rod. But if you see here the variable of x, if you consider this small portion here, then the value of x will be 0. Similarly, if you consider value of x will be something different like this. If you take the value of x from 0 to L, then we will find out the moment of inertia of each portion of the rod. And then integrate it. Integration means sum up. Then we can determine the moment of inertia of the whole rod. Integration means what? To sum up. Let this equation be 1. If we integrate this equation by taking the limit of what is variable here? X. Because m, mass of the rod, and L, length of the rod, is fixed, constant term. These two are constant. Only variable term is x. So integrate what? Integrate this equation. By taking the limit of x from 0 to L, then we can determine the moment of inertia of the whole rod. Now, see here, we are doing here integrating equation 1. Integrating equation 1 What is the limit of integration? What is the limit of integration? M by L constant term, keep it outside. M by L constant term, keep it x square into dx. X square into dx. Now you see what is the limit of 0 to L. That is 0 to R. Total moment di integration of di is what? I 0 to I. That is I minus 0. It is I. No. M by L x square into dx. What is the integration of this power is 2? So power will be 3 n plus 1. What is n? 2. So according to integration formula, power increases to 1 unit and power comes here. No, no. This is mod. What is the lower limit? 0. Upper limit is L. We are integrating this equation from 0 to L. Then we are covering each and every part of the rod. And then here we are determining the moment of inertia of the whole portion of the rod. Now you see here. What is the integration of this portion? I minus 0, it is I. Moment of inertia of the whole of it. M by L. What is the upper limit? L. 3 comes out. Constant term comes out. Now, what is the upper limit? L. First put upper limit minus, then put lower limit. What is upper limit? L. L cube minus, what is the lower limit? 0 cube. 0 cube is 0. So it is moment of inertia of this rod is m by 3L into L cube. L cancel out, L square left. The moment of inertia will be m L square upon 3. This is the formula for moment of inertia of a rod. Moment of inertia of a rod about the axis passing through one of its end. That is ml square upon 3. This is what? ml square upon 3. Now, in second case, we will determine the moment of inertia. In second case, we will determine the moment of inertia of the same rod, but the axis will passing through its perpendicular bisector of its length. See here. In second case, moment of inertia of rod about axis passing about axis which is perpendicular bisector to its length, which is perpendicular bisector of length, perpendicular bisector of length. Now you see here, we are restricting here. See here, this is the rod. Again, this is the axis of rotation. Since rod length is 0 to L. Now we will not take 0 to L. Total length is L. So if the axis is passing through its center, take origin here. From here to here, its length is plus L by 2. And from here to here, from my L length will be minus L by 2. So how we can determine its length? Again, move to distance x, take a small portion dx of the rod in which mass dm is present. Now again, comes here. So di is equals to m dm into x square. What is the limit? What is the limit? Minus L by 2 to plus L by 2, it will cover whole distance. What is the length of the rod? L. But the axis of rotation is passing, but the axis of rotation is passing from where it is passing. The axis of rotation is passing through its perpendicular bisector of its length. So this side length is L by 2, this side length is L by 2. L by 2 plus L by 2, L. That is the total length of the rod. That's why we taken here limit minus L by 2 to plus L by 2. So here the limit of integration will be minus L by 2 to plus L by 2, 0 to y. Moment of inertia I is equals to, what is the value of m? Dm m by L into dx into x square. Now keep it outside, integrate this equation taking the limit of x from plus L by 2, minus L by 2 to plus L by 2. Now I is equals to m by L. What is the power? 2. 2 we can write like this, x square into dx. Now power is n, so it will be n plus 1, that is 2 plus 1, 3 upon 3. Now minus L by 2, lower limit, upper limit plus L by 2. Now put this value, m by constant, take it outside, 3L. Now put upper limit, what is the upper limit? L by 2 ka cube. L cube upon 2 cube, 8, minus, what is the lower limit? Minus L by 2 ka cube, since this is odd. So power remains, sign remains minus. If even 2, 4, 6, 8 like this, then this becomes positive. Minus L cube upon 2 ka cube, 8. Now this equation becomes minus minus plus 2L cube upon 8, 3 is 24. 8, take LCM. If you solve this, m by 3L minus minus plus 2L cube upon 8, that is 4, 4, 3 is 12. L cube, L square comes, that is answer, your answer will be, first is like this, m by 3L 8 2L cube, like this, 2, 4, 4, 3 is 12, L square. So your answer will be, your moment of inertia, formula for moment of inertia is m L square L cube, 1 power cancel out. The formula will be m L square by 4, 3 is 12. 4, 3 is 12. So formula for moment of inertia is ml square upon 10. Whereas in previous case, when we have taken the moment of inertia of the same rod about the axis passing through its end, passing through one of its end, its moment of inertia was ml square upon 3. Now here, when we are passing the axis through its perpendicular bisector of the same rod, the moment of inertia decreases. Moment of inertia decreases. That now this time it becomes ml square upon 12.